Okay, welcome everybody to chemistry here. Today we're going to talk about what happens when we have a weak acid. So remember, a strong acid, we generally said that all of the protons come off of the acid, it completely dissociates. A weak acid, though, is different. It doesn't want to let go of its protons so much, so it doesn't dissociate. In fact, acetic acid here, if you can see this acetic acid right here, that's vinegar. And this, you can see, has one proton. And basically, for every 100 pieces of vinegar, I'll get one proton. So about 1% of acetic acid will dissociate when added to water. This number here is what we're going to be using for our math today, and that's called the weak acid dissociation constant. Okay, and the formula for that then is a relationship here between the acid particle and the proton and the base molecule, or the conjugate base, you could say. So if you look at this acetic acid formula here, what we usually typically do is we take this base of the acid and we call that A. So we can just kind of have the same formula for all the acids. And then H would signify the proton that's going to be coming off. So when this dissociates in water, this constant here is going to have this general form of a product of the proton that is actually dissociated, and then the other part of the acid, which would then be a negative piece. And then underneath, it's divided by the conjugate base is really what it's supposed to be divided by. For our purposes, we'll just use what we started out with. I guess in AP chemistry, you'll find out that there's a 5% rule. If the difference between this and this minus this is less than 5%, then it's negligible. You don't have to include that in the math. And for us, we're not going to use a quadratic formula for this, so we're going to stick with our formula as being a little more simple than this, which the differences will be negligible at this point. And this will be the proton, the number of protons, which if it's a monatomic acid would be the same number as the negative base that came from. And I mean base molecule, I don't mean base. And then this here, we'll just use the concentration of the beginning acid that we started with. Okay, so as we're looking at this acid ionization constant right here, there is a table in your present book here on page 602. And something I want to look at here is how this changes. So if you take arsenic acid here, you can see the arsenic acid. It's what we call a triprotic acid. This would be a diprotic acid because there's two, and then this is the monoprotic acid. There's three vocabulary words for you, but you're familiar with these prefixes, so that should be no problem for you. But this is all coming from the same arsenic acid. So if we put this in water, this is our relationship here, or our acid constants. And so you can see that it's 6 times 10 to the negative third. But then when it releases one of its protons, then what happens is this negative part is more attracted to this positive part, so it's harder to release the protons. And you can see that the constant here for the diprotic portion of this arsenic acid is less. It's 1 times 10 to the negative 7th. In fact, it's much less. The difference of these powers are drastic. And then you can see down in the monoprotic, it really doesn't want to let go of that last proton, and that's even much less. And that's all has to do with electronegativity. Each time it leaves, one proton leaves, it leaves us with a more negative charge here. And then, of course, these negatives are attracted to the positive proton, so it's harder to let go of each proton as you go on down the line. Okay, so we're going to take a look at just some of the math. Like I said again, the K sub A is called the weak acid dissociation constant. And you'll find that in your book on page 602. And so this is the general formula. The proton, after it's put in water, the dissociated proton, and the base that the proton leaves behind, divided by, and like I said, for our purposes here, we're just going to go with the amount of base that we started out. And all these amounts are in concentration, molar concentration. Okay, so that's our general formula. Let's take a look and see how that works. We're going to start with methanoic acid. So let's say that we have a vat of methanoic acid, 1 liter, and we find that we have concentration, or we put in 0.1 moles of methanoic acid. So we have methanoic acid here, and we have an amount of 0.1 moles. And we put that in, and we end up with a 1 liter solution of this water and 0.1 moles of methanoic acid. Okay, so from our constant table, we can say that the Ka of methanoic acid is 1.8 times 10 to the negative 4th. And if you look at this formula, what we can see is we're going to have our methanoic acid, and it's going to split up into the positive proton, and then the negative base, which will be COOH. Okay, so the question is, we put in 0.1 moles of this. How much of this do we get? How much of this do we get? Okay, so if we look at our formula, we can set it up as this Ka is equal to the H plus times the A negative, the concentrations, divided by what we start out with for our purpose. And we can say, if we do the math here, that 1.8 times 10 to the negative 4th is equal to, now we don't know what this number is. We don't know what this number is. But what we do know is they are the same number. So we can just put in a variable of x here. X times x then equals x squared. Okay, and that's going to be divided by 0.1 moles per liter of our acid. Okay, so then we just go through and we solve for x. So we have to multiply both sides by 0.1. And we can see over here that we have 1.8 times 10 to the negative 5th equals x squared. Okay, because we cancel this out, multiply both sides. And so, to solve for x squared then, all we have to do is take the square root, and the square root of 1.8 times 10 to the negative 5th is 4.243 times 10 to the negative 3rd. And that would be equal to the number of protons per mole in there, and also the number of the negative acid base per mole in there. So now, of course, the next question is pH. And just to reiterate how we did pH from yesterday, pH is equal to the negative log of the proton concentration. So the pH in this case is going to be the negative log of 4.243 times 10 to the negative third. And the pH in this case is 2.372. That should help you do your worksheet and your assignment. I can go through another example. This one will be a little bit faster because I'm running out of time. But so I've got 0.02 moles of HCl, and I put that into a vat of water, and I come up with a 1 liter solution. So my question is, what is the pH of this solution? Okay, so we'll start out as we did before with our balanced equation here, or our representation of what's going to be happening during this dissociation. Okay, and then I set up my equation. My Ka is equal to the product of my positive and then negative pieces. And for us, we're just going to divide it by the acid concentration here. So in this case, it would be just what we started with. Okay. So our Ka for this is 2.88 times 10 to the negative 8th. And that's going to equal, like we said before, these have to be the same number because they come from the same piece, and there's only 2 pieces per big piece. So it's going to equal x squared, and it's going to equal, or it's going to be divided by what we started with here for the moles, which will be 0.02. And if we go ahead and solve for x squared, we can see that we have 0.02 times 2.88 times 10 to the negative 8th. Take the square root of both sides, and we'll see that our x, we'll see that our x then is equal to 2.4 times 10 to the negative 5th, and that's our x, which, like we stated before, is going to be our concentration of protons. And then what we do for that to finish this off, let me erase some of this, is we just take the negative logarithm of that, okay, so the pH in this case then is equal to the negative log of 2.4 times 10 to the negative 5th. And that pH then becomes 4.62. And that's how you determine the pH of a weak acid. Now, we also have weak bases that we'll talk about, but it's the same principle. All the method's the same, it's just you're using a base instead of an acid. Okay. Thank you.